Here's the explanation for how we can use Google Sheets to help us determine the size of the DNA fragments that we have in our gel electrophoresis. So I want to give you a little bit of background before we start. If you just take how far the DNA has migrated on the gel that we have here, this is in millimeters, and we compare it to what we know the fragment sizes to be, because this is lambda DNA cut by the restriction enzyme Hindi. We can use that to make a standard graph. Now, if we just graph migration compared to fragment size, we get this exponential equation. And if you look at the R-squared value, it's only 0.941, which I'd really like it to be a little closer to 1. So one thing that you could do is graph it on semi-log paper. That would get it to look more like a line, or since we're in Google Sheets, we could also graph the migration compared to the log 10 of the fragment size. You see, it gets to look a little bit more like a line, but still my R-squared value is only 0.941. So another thing that I can do is graph 1 on migration, or 1 divided by migration, compared to the log 10 of the fragment size. And if you look at this line, the R-squared value is 0.996, which is much closer to 1, and so really a better fit for the data. And then I can use the standard equation of a line of y equals mx plus b, where x represents 1 divided by the migration, and y is the log 10 of the fragment size. And then I can use Sheets to figure out what the actual fragment size is for my unknown bands in my gel electrophoresis results. So let's take a look at how we would do this on our Google Sheet here. So you, as a class, we measured the migration of the lambda DNA that was cut by Hindi. And so here are our measurements, and we know the fragment sizes. This is a known one. So the first thing I'm going to do is I need to figure out 1 divided by migration. So I'm going to use the formula capabilities. So that's 1 divided by, and then the migration. And there we go. And then I want to apply that formula to all of the cells. We'll get my little plus sign, and there we go. Now I also need to find the log base 10 of the fragment size. So again, I'm going to do equals. I'm going to start typing in, there's log base 10 of my fragment size, and I let Google Sheets do that for me. I'm going to apply that to all of the cells that have to do with the fragment sizes. All right, now I don't even need to graph this. I know this is going to give me a good line. The trend line is going to be a good fit to the data. So I can really, all I need to know is what's the slope and what's the y-intercept, so I can plug it into the formula to find my other fragment sizes. So again, Google Sheets has a formula for this. So I'll type in slope. Okay, and I need to do, the first slope is y over x. I'm going to do my y values and separate it with a comma over my x values. Okay, and there is my slope. It works the same for the y-intercept. I will type in intercept. There it is. And again, I need my y values, and I'll separate them from my x values. Okay, and there's my y-intercept for my equation of the line, y equals mx plus b. Now that I know what my slope and y-intercept are, I can apply this now to other gel electrophoresis of lambda DNA. This one was cut by BAM-HI, and so here is this, let's see, 5 bands that we got. We went ahead and measured how many millimeters they were away from the well, and so again I need to go through the process of finding 1 over the migration. So let's get our equal sign. And we have 1 divided by the migration. And I'll apply that formula to all of my cells. And I'm going to go ahead and increase my decimal places just for a little bit. I'll put them back down later. I also need to find the log 10, or actually, I can't find the log 10 of my fragment size. That's what I need to use my formula to do. So I'm going to use the log 10 of my fragment size should be the y of y equals mx plus b. So I use my equal sign. So it equals the slope, right, times x. So here's times, x is 1 over migration, and then plus the y-intercept. And so this is my log 10 fragment size of this band in my gel electrophoresis, or that, really of that fragment of DNA that happened to be in that first band. We're going to increase my decimals. Fix that later. Now before I drag this down to apply it, I want it to be looking at the cells as they go down, but I don't want to change what cells they're looking at in the slope and for the y-intercept. So I'm going to go into this, and I'm going to put a $sign in front of this so that it won't change what cell that it's looking at. I don't want it to change the row or the column, so I'll put $signs there for the slope. And I'm also going to put $signs for the intercept because I also don't want the cell for the intercept to change. All right, now that that is complete, I can apply this formula to all of the other cells in this row. Okay, and it gives me now, here's the log 10 of the fragment sizes that were in each of the bands of my electrophoresis gel. Now, but I don't want to really know the log 10. What I'm interested in is how big are those fragments of DNA that were in each of the bands in my gel electrophoresis. So my last step is to now convert this back into base pair fragment size, which is in kilobases. And so, again, I'm going to do an equation. So I use my equal sign. There we go. And that needs to be 10 raised to the, so I'll do shift 6 to get my caret, raised to the log base 10. And that will convert it into base pair size. All right, and then I need to apply this to the rest of my cells. And now I know my sizes. If I want, I can take these cells and decrease the decimal. In fact, I think I'm going to decrease it to whole numbers. And there you have it. So now you know, even without having to make a graph, you don't have to pull out your ruler to estimate, you know, where your y value would fall. You don't even need to see the graph. You can just use sheets and formulas to figure those out. So now I know all of my DNA fragment sizes that were in each of the bands. Hope that helps.